We have discussed the doping process of a standard P-type wafer-based crystalline silicon solar cell. However, these days more and more solar cells are produced on N-type wafers instead. In this video we will show how P-type silicon became and still is the market leader for terrestrial photovoltaics. We will then compare some properties of P-type and N-type wafers that could lead to an industrial shift from P-type to N-type in the near future. In the 1960s and 70s, the only commercial market for photovoltaics was the space industry. Development of solar cells was therefore not focused on terrestrial applications, but the cells were sent into space. Both N-type and P-type wafers were researched, and N-type cells would show a better initial performance over P-type solar cells. Controlled irradiation studies, however, demonstrated that the minority carrier lifetime of N-type cells degraded significantly. P-type wafers were much less susceptible to space radiation, so the choice was obvious. From there on, the entire processing chain of casting ingots, wafer doping, emitter diffusion and metallization was developed for P-type based silicon solar cells. We will now compare the electrical properties of P-type and N-type wafers. An important parameter here is the minority carrier lifetime, as this plays an important role in determining the photo-generated current density. The electromobility in silicon at room temperature is about 3 times higher than the hole mobility. A higher mobility implies a higher diffusion coefficient, d, via the Einstein relation, and thus results in a longer minority carrier diffusion length. In P-type silicon, electrons are the minority carriers, and therefore the minority carrier diffusion length is superior to the minority carrier diffusion length of holes in N-type silicon. This would be an advantage for using P-type silicon, but there is one issue. P-type silicon is vulnerable to metallic impurities such as iron, titanium, vanadium, molybdenum, manganese and cobalt. These impurities result in a reduction of the minority carrier lifetime. N-type silicon is less vulnerable to metallic impurities caused by a difference in the impurity capture cross-section for electrons and holes, ultimately leading to longer lifetime for minority carrier holes in N-type silicon. The underlying physics is beyond the scope of this video, but it results in a superior minority carrier diffusion length, even though the minority hole mobility is lower. Moreover, while moving towards higher purity grade and thinner wafers, the minority carrier diffusion length starts exceeding the thickness of the wafer, placing more importance on front surface engineering. There is another issue with P-type wafers, which is light-induced degradation for silicon containing both boron and oxygen. During Swarovski casting, the most used method for making crystalline silicon, oxygen from the quartz crucible will enter the silicon melt. On one hand, this is desirable since oxygen will increase the strength of the wafer, but on the other hand, the oxygen creates metal-stable defects leading to energy levels around the middle of the band gap when being exposed to illumination. A partial solution would be to lower the oxygen content in the silicon ingot. These methods are more expensive, as we have seen with float zone pulling. In this case, any contact with a quartz crucible is avoided. Another option is to replace the boron dopant by other P-type doping elements such as gallium or indium. Again, this will increase the price of a wafer significantly. The most obvious solution to light-induced degradation is then to switch to N-type silicon wafers, where boron might only be present as an impurity. So far, the electrical properties of N-type silicon are superior to P-type silicon. So the question arises if there aren't any downsides to using N-type silicon wafers. There are indeed some downsides to using N-type silicon, which originate from the ingot doping process. For Swarovski casting, the dopant is directly added to the silicon melt. While pulling the crystal, there is a difference in doping concentration between the solid phase and the liquid phase. The ratio between these concentrations is defined as the segregation coefficient K0. The value of this coefficient is smaller than 1 for most elements, meaning that dopant atoms are rejected back into the liquid phase, effectively increasing the doping concentration of the melt. For K0 equals to 1, the doping distribution in the crystal will be uniform. Boron has a K0 value of 0.8, while phosphorus has a K0 value of 0.35. A more uniform can be obtained by continuously mixing pure silicon into the melt to maintain a stable doping concentration. Nevertheless, phosphorus doping leads to a crystal formation with a wider resistivity distribution in between 3 to 12 ohms centimeter compared to boron doping, with a resistivity in between 1 to 3 ohms centimeter throughout a single crystal. This implies that the yield of good quality N-type wafers is reduced and that the price of N-type wafer production is therefore higher. This figure shows that N-type silicon solar cells are projected to obtain a larger market share. The prospects for the near future also look very promising. Production processes are rapidly improving, which also results in a price reduction, closing the gap to P-type cells. To summarize this video, the current silicon PV market is historically dominated by P-type based solar cells due to their better resistance to space radiation. We have discussed that for terrestrial applications, N-type wafers have superior electrical properties such as a better minority carrier lifetime and no light-induced degradation. The processing of N-type wafers, however, lags behind on P-type and needs more development. The drive behind this development is the potential to yield record-breaking solar cells with a competitive price tag.